Okay, in this video we're going to talk about rates of change, and I want to start with an example. Einstein is riding his bicycle. At 1 p.m. he's traveled 20 miles, and at 3 p.m. he's traveled 60 miles. What is Einstein's average speed on his bicycle between 1 and 3 p.m.? Think about it for a minute and see if you can come up with the right answer. Okay, so the correct answer is going to be 20 miles per hour. There are a lot of people that can get the answer 20 miles per hour, and to some people it even seems like a fairly simple example. But there's a lot of calculating that goes into this even very simple problem. Let's think about how you got that answer. What most people would do is they would say, okay, I started at 20 miles and I ended up at 60 miles. So the total number of miles that I've traveled is 40. And you get that by doing 60 miles minus 20 miles. And then you would look at the times and you'd say, okay, I started at 1 p.m. and I ended at 3 p.m. So that means I took 2 hours. And really the calculation that you have to do to get that is you have to subtract 3 minus 1. When you do the subtraction, 60 minus 20 gives you 40 miles. And in the denominator you have 3 minus 1, that gives you 2 hours. 40 divided by 2, of course, is 20, and miles divided by hours is just miles per hour. The miles per hour at the end of this problem, these are called the units of the answer. And units turn out to be very important in these types of rates of change problems. We're going to talk a lot more about units a little bit later, but what I want to do first is I want to look at this problem in a slightly different way. What I want to do is I want to set up a graph of Einstein's progress on his bicycle. So I've set up a graph here. On the horizontal axis, I have time, 1 p.m., 2 p.m., and 3 p.m. On the vertical axis, I have Einstein's distance in miles that he's traveled on his bike. So what we can do is we can look at this first piece of information. At 1 p.m., he has traveled 20 miles. And we can look at the graph and say, oh, well, that 1 p.m. traveling 20 miles would put Einstein right here on our, on our XY plane. And you'll see right away that what we've done is we've taken this piece of information here and we've turned it into a point. We've turned this into the point 120. Now I'm going to erase that point from our graph to keep things kind of pretty. But can you come up with another point from the information? Well, yeah, at 3 p.m. Einstein has traveled 60 miles. So that gives us a point. At 3 p.m. he's at 60 miles, which would be right there. So what we can do is we can connect these dots with a line. And if we do that, we draw this line right through those 2 points, and we get a line that could represent Einstein's progress on his bicycle. So the question that I want to ask is, what is the vertical distance between Einstein's 2 points? So you can look at the y values of these 2 points. This highest one is 60, and this lowest one is 20. And you can figure that the distance between those 2 points is 60 minus 20. Now, what is the horizontal distance between these 2 points? Well, you can look at the 2 x values to get that horizontal distance. You'll notice that Einstein starts at 1 p.m. and goes all the way to 3 p.m. That distance then is 3 minus 1. Of course, the units on the 60 minus 20 is going to be miles. And the units on the 3 minus 1 is going to be hours. So these numbers are starting to look a little bit familiar. They're starting to look like our first calculation of Einstein's average speed. To get Einstein's average speed, all we have to do is divide the 60 minus 20 by the 3 minus 1. 60 minus 20 miles divided by the 3 minus 1 hours. If we do that calculation, we get 60 minus 20 is 40 miles, and we're dividing by 3 minus 1 is 2 hours, or 20 miles per hour. So really we did the same calculation twice. So what we just did is we found Einstein's average rate of change on his bicycle. In this case, it was measured in miles per hour. Now the calculation that we just did is actually a very important calculation in math. What we did was we took the vertical distance between these 2 points on a line, and we took the horizontal distance between the same 2 points on that line, We divided the two answers. That calculation is actually called a slope calculation. We found the slope of this line. Now we're going to talk a lot more about slopes in this video and in probably the next video as well. But what I want to do first is I want to talk a little bit more about units. Now remember what I said earlier. I said that the units on this example were the miles per hour. So Einstein's average speed, or his average rate of change in this case, was measured in miles per hour. There are an endless number of possible units that we could have with these average rate of change calculations. I'll scroll down to show you a few examples that I came up with. Miles per hour, that's the example of the units that we just did. Minutes per second would be another way to measure velocity. Gallons per year would be something like how much soda do you drink? Miles per gallon would be a question of how efficient your car runs. How many miles can you go on 1 gallon of gasoline? Tons per day, maybe that would be a mining example. How many tons of rock do you dynamite in a day or something like that? Transactions per day, if you're maybe a cashier and you wanted to measure how fast you worked, you might look at something like how many transactions do you do in one day? So those are just a few examples of an infinite number of examples of possible units for these types of rates of change calculations. Now let's look back at our example. Our units were miles per hour. And you'll notice that on our vertical axis, in this lower calculation that we did, we have the units miles. On our horizontal axis, we have the units of hours. It's time in that case. This is not a coincidence. The unit in the numerator is always going to be on the vertical axis, and the unit in the denominator is always going to be on the horizontal axis. Let's look at another example. In this example, we're looking at a graph of the cost of a gallon of milk over the last 12 years. In 2000, the average cost of a gallon of milk was $2.88. In 2012, the average cost was $3.53. My question in this section is, what is the average rate of change of the cost of a gallon of milk between 2000 and 2012? Let's look at the graph and figure that out this time. What we do is this. We look at the vertical change between those 2 points. And in this case, we started with a vertical value, a y value of $2.88, and we ended with a y value, or vertical value, of 3.53 cents. So this distance between these 2 points is going to be 3.53 minus 2.88. Let's also look at the horizontal distance between these 2 points. Of course, we started in 2000 and ended in 2012. So the horizontal distance between these 2 points is 2012 minus 2000. The units, of course, on these vertical numbers, they're both measured in dollars. And in the horizontal units, they're both measured in years. So let's do the calculation. Now remember what we did in the last example is we took the distance between the points in the vertical direction and divided the distance between the points in the horizontal direction. So let's do that. What we have now is 3.53 minus 288 divided by 2012 minus 2000. Subtract the two numbers in the numerator and you're going to get 0.65, I believe. Subtract the two numbers in the denominator and you're going to get 12. Do that division, you're going to get approximately 0.054. And what are the units on this? Well, in the numerator, the whole time these units were measured in dollars. So that would be dollars. In the denominator, the units were always years. So what does that mean? Well, it means that the cost of milk has gone up by $0.054 per year. Is there a more convenient unit for this, something that might be a little bit more understandable? Well, yes, $0.054 is just 5.4 cents per year. So the average rate of change of the cost of a gallon of milk between 2000 and 2012 is 5.4 cents per year. The cost of a gallon of milk has gone up on average 5.4 cents per year. Okay, let's get you guys a video quiz. Take a look at the graph below. It represents U.S. oil consumption in billions of barrels used per day. So these numbers here on the vertical axis, 16, 17, 18, they represent the number of billions of barrels of oil that we use per day. On the horizontal axis, you have several years. Now there are two questions here. Find the average rate of change of U.S. oil consumption between 1980 and 2010, and also find the average rate of change of U.S. oil consumption between 1990 and 2000. Don't forget to label your units. Now the units are a little bit tricky in this example, but see what you can do. Good luck, and I'll see you in class.